And
hi all. Welcome. Don't call out because it might interrupt me. Never mind. In a virtual world, there is no audience. But please feel free to type in questions, and Naveem is gonna moderate for me, and I'll try and answer the questions if they come up during the talk. But I welcome everything. This is a tour de force talk. I'm going to cover a lot of material, lot of different technologies, because Kubernetes touches a lot of things, and Kubernetes storage touches even more things. Again, as my background, I'm president at AuriStor, but I'm a hands-on president, and have written the Kubernetes CSI Driver. So without further ado, I'm going to share my screen, and Naveem, can you confirm that my screen is up? Somebody? Did somebody confirm my screen is up? I'm going to assume it's up then, because nobody's saying anything.
Hi, sorry, I was on mute. Yes, your screen is up.
Great. Okay, so let me get going now. And before I do, let me just do a little time check. And yep, just one of my coworkers said it was up. And okay, there you go. So now you're seeing my entry slide. Before I get started, in case you missed a talk earlier today, 1:30 on the Eastern time and 11:30 in Central time, Tracy DeMarco White, who's at Goldman Sachs, gave a really good talk on software and software deployment, bigger on the inside, where she talked extensively about how they distributed software, in particular using an AFS family product called AuriStor file server, AuriStorFS, which happens to be the product that my company produces. But I recommend taking a look at Tracy's talk. I know it's already online, recorded. So I'm going to cover a lot of stuff. I'm going to cover containers. I'm going to cover Kubernetes, a little brief introduction to Kubernetes. Then I'm going to do a deeper introduction of what's the Kubernetes API model. I'm going to give a little history of Kubernetes storage, which is pretty ugly, but now it's pretty. And then I'm going to go the big chunk of the talk about understanding Kubernetes storage. I'm going to then talk a little bit about the Andrew file system family of distributed file servers, AFS, and AuriStorFS, OpenAFS. Tracy gave a little bit of actually probably deeper coverage of it than I did. I'm going to kind of do more of a hand wavy one. And then I'm going to really dive into what I learned and what's going on the inside of the writing a container storage into Kubernetes driver. For those of you who ever have seen me talk before, you'd know that I have a philosophy of software, because I've built a lot of distributed systems, but even when I'm using any software, I have a philosophy: never use any software that you don't know how to write. Not that you're going to write it, but that you could write it. And a corollary to that is you never learn an API. You discover the APIs that you know have to be there. And it took a lot of unwrapping to get that depth of understanding with Kubernetes, but I'm going to share some of that perspective, and that's going to be invaluable in understanding how to build, debug, maintain DevOps, administer Kubernetes clusters, in particular having to do with storage. So for those of you who know approximately nothing about containers, here's my one slide coverage of containers. Containers are actually, there's a lot of noise around containers, but really fundamentally it's about software distribution. We've traditionally had software, we've had a tar file, and we put the tar file on some server, we untar it, and we start something. So it's a way of getting things distributed. So it's analogous to a tar file plus a runtime framework. So that compressed image in the container world is called a container image, and that's the unit of deployment. It's just a bunch of bytes. It's just a bunch of bytes. You then have a container runtime, for example, Docker, which is what most people are familiar with, or Podman coming out of Red Hat, that know how to take that bunch of bytes and create a running container based on that image. For those of you who don't understand why containers, containers kind of are like as if you were running a VM, but on your local host without the heavy expense of maintaining a VM or startup costs. So what it really does is that there's a whole bunch of setting up your network, setting up your disk, setting up your file system to look like you're on your own machine. And then once the setup is complete, it just calls the Linux init function. So that's why you can have any Linux deployment, because every Linux boots up the kernel and then calls init. You know, the Linux init function. You create an image which has an init function, but you don't have to do the setup because you're relying on the kernel that's on your host system. And so basically it's just run as processes on your local host, on your local on the host machine, and inside the running container, it appears as if you are on your own host, disk, network, etc. And again, this is done with Linux namespace magic. So now that we're experts on containers, let's talk about containers and storage. If you think about it, when you design an application, you design an application to run, and it often expects some files to be there, configuration files, data files, executable files, whatever. It expects the files to be there. But so the idea with containers is you have that bundled container image, which encapsulates a frozen snapshot in time of what the disk looked like on a system. But so you have all of those files available at runtime. But you don't want to necessarily bundle everything in, because you'd have to have this version of my app with this configuration file, this version of my app with this data file. That would be way too many containers. So there is this idea that you can also mount volumes to a designated path in your container. This is the first use of the word volume. Volume is such an overloaded term in storage, and I'm going to use volume many times in many contexts, and they don't always mean the same thing. I'll try to be clear. So when you design an application, there's two aspects. The application author knows where it's expecting a directory to be that's going to have files that it's going to read. Now, what's in that can be determined in the container world by an administrator that can mount into the container something else. So for example, look at this in the green below. I assume you can see my cursor. I just happen to have a local directory called zoo on my home path. It has bears, monkeys, and zebras in it. For those of you who know how to run Docker, you say Docker run blah 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 -v ~zoo : /animals. So what is that actually saying? It's saying that, sorry, excuse me, I wanted to actually run this, and I realized I need to get it in my copy buffer. Sorry about that. So what does that statement say? It says run an image of Fedora, plain Jane Fedora, but I want to have a path animals in the launched VM, and I want what's in animals in my container to have the contents of actually be my local directory zoo. And the last bit is the command you're going to run. So let me of course, somewhere, there you go. All right, I'm going to bring in this. And so there's that command. And notice that I'm running not in a directory with my animals. Dang, I forgot where I put my animals. So I'll make a directory animals. I'll make a directory zoo, I'm sorry, zoo, and, oh, it is there. Never, okay, touch zoo / monkey. What the hell is going on? Demo land. Okay. I think I know why. Fine. Make their cages. We'll cage our animals. Touch. I'm not going to explain what's going on. It's a permission thing. Cages / monkey and cages / bear. And now I will run the command that I had a second ago. And I'll run that command that I had a second ago. Here it is, except because I was having trouble, I'm going to have it mount my local directory called cages. And now if I look on this machine, there's an animals directory. And if I ls animals, lo and behold, there's the files. And in fact, if I don't remember how I set it up with permission, but if I touch animals / giraffe, and I exit the VM and I look at my cages, lo and behold, there's a giraffe. So I basically said, take that local directory and mount it as if it was in that place in my running container. We're going to revisit that a lot in the Kubernetes world. And again, it didn't have to be a local directory. It could have been some NFS mount. It could have been anything. I just happened to link in a local machine, a local directory. So now, for those of you who know approximately nothing about Kubernetes, it's a framework for launching and managing containers. So it's a distributed system running across a bunch of clusters. I've got these N machines that I want to be able to distribute some number, a flexible dynamic set of containers in this Kubernetes cluster based on some restrictions and requirements, et cetera. And Kubernetes does the management. So that's really all it is a management system, but it does a lot of very cool stuff to do it. It does the scheduling, it sets up overlay networks, it does load balancing, auto scaling, monitoring, lots of good stuff. If in this talk or anywhere in the world you see the letters, the initials K, not the 8S, K8S is Kubernetes. Okay, so if I wrote that, you'll know what I'm talking about. Okay, so now Kubernetes. We're really used to imperative APIs. You call a function, and whether it's a local function or a remote function or a REST call, and you're blocked until it returns. That's what an imperative function is, and that's a really not well-suited way to do things that are things that are like things that administrator would do. Because think of what Kubernetes is doing. It's doing a lot of the work a system administrator would do. So for example, one of the reasons you don't want an imperative API is things may take a long time to schedule or set up, or they may never be scheduled, or they may need some interaction. So you want to say like run, and then you're kind of blocked until something happens, resources free up, et cetera. So what the Kubernetes model is instead using what's called a declarative API. And what a declarative API is, again, everything uses the word objects. In the design pattern of a declarative API, you have an object that has 3 fundamental properties. Actually, in this case, there's 5. But first is what kind of object is it? And a specification for the state I would like that object to be in. The state that I would like it to be in, not the state it's in, the state I would like it to be in. And we'll revisit that in a minute. But what you see there is collapsed YAML. So now in Kubernetes uses a declarative API, and it has objects. And one of the daunting things about Kubernetes to get started is there are 55 different kinds of Kubernetes objects in the current version 1.19. Some of them aren't really used anymore, but they're on the way to being deprecated. But 55 is a large number of things that can be specified. Now it turns out a lot of them are done behind the scenes or created for you. But what I have here is a list of ones that you really should kind of be aware of. And it's still a lot. There are ones that do the actual creation of containers, and I'll go back into that later. Pods, deployment, stateful sets, daemon sets, replica sets, cron jobs, and jobs, where deployments, where a pod is sort of a single unit, run until it stops. Deployment is run n of these things. A stateful set is run an ordered set of n of these things so that you can do things like remapping to storage. Daemon set is run one of these on each of the worker nodes in your cluster, et cetera, et cetera. Now, storage is particularly complicated too, because there's a lot of storage objects. There's persistent volume claims, there's persistent volumes, there's volumes attachments, there's storage classes, the CSI Driver, the CSINode, volume snapshots. Oh my. It's hopefully at the end of this talk, you'll understand this a lot better. But the things in red, I don't know if I do have an example with it. I'll only show events if I have a problem with my demo, but the things in red will be touching. So these are all different kinds of Kubernetes objects. So there's no container object in Kubernetes. No container object, which seems really odd because it's a container orchestration system. And there is instead is a pod, which is the basic unit of management. A pod can have one or more containers. And that kind of makes sense for certain things like you might want in the same pod one container that's downloading weather content and generating images, and the web server that's serving it. So you kind of deploy them together because they're kind of bound together. The thing about containers, pods, is when they're running in the same, when you run two or more containers in the same pod, they share localhost. So you can't use the same port by two of the containers in the same pod. And you can mount storage like we just talked about. And that storage can be available to one or more of those containers. And I just mentioned that the Kubernetes objects that create pods are deployments, blah, blah, blah. Stateful sets are the ones that are mostly used with storage related things. And that's historical, and I'm not going to go so deeply into that because I want to talk about storage itself. So talking about Kubernetes, so you've got an API. Well, if you have an API, you need a server for that API. And in Kubernetes, there's an API server. And the two basic ways to access it are with a command line tool called kubectl, Kubectl. And then there's a REST API, and there's a binding for Java and Python and Perl and Go and blah, blah, blah. But effectively, it's a RESTful API that you take these objects that I just showed earlier, a YAML object and a JSON object can kind of be converted to each other one-to-one. So there's a RESTful API where you create an object, you post it to the server. You can also post updates. You can watch for changes. You can delete objects, et cetera, et cetera, et cetera. You post these objects that are stored in a persistent key value store. There's a zillion of them out there, but they use one called etc, if you're familiar with it. And the only thing the API server does nothing. The API server does nothing except respect that RESTful API, with one exception. There's a hook in it that you can, for every Kubernetes object, you can hook what are called admission controllers. And all these admission controllers do is for example, a new Kubernetes object is posted to the API server, before it gets to etc, it goes through a series of validating admission controllers. And what they do is they just make sure it's well formed. Are there in fields I don't understand? Are there fields with invalid options? It can't do a deep study of it, but it can do sort of a well-formedness study. And then there's something called mutating admission controllers. So for example, you don't want to do validating in general on your server. You want to get like totally populated input. So for example, if there's defaults that you don't want the user to have to specify, but you have a mutating admission controller that will sort of poke in the defaults if the object that was posted didn't have the defaults. So we now have a system that does nothing. So what goes along with the declarative API is something called the operator pattern. And with the operating pattern, you have these helper things that help move your objects from your desired specification into from the specification, move the object towards the desired specification. And it's a state machine, and it stores the state in the status. Okay, so the status is where the object is, the spec is where you want it to be. And so what these operators do is they'll listen to these objects and they'll say, oh, there's a new that kind of object. What does it need to move towards its state? Oh, some helper objects need to be created. So I'll create those helper objects and I'll post them to the API server, and I'll wait till they're ready. And when they're ready, I'll then take that object that the original object, and I'll patch it, I'll update its state. And so it moves it along its state. So that's the operator pattern. It's just these external operators that are kind of act like software administrators, and they move them along their way. There are two other things that watch the API server. Arguably, they're just another example of an operator. One is the Kubernetes scheduler. Like, when do things get saying, okay, now it's ready to run this pod on that node, and the kubelet. And what the kubelet is that's the thing that actually creates the containers on your local, on each of the worker nodes. You'll see here the word controller. Historically, in the Kubernetes world, controllers are operators that are core Kubernetes operators. And then they realized, hey, and it used to be one monolith application, and slowly but surely they're taking all the controllers and making them into external operators, so the system is easier to maintain, and et cetera, et cetera, et cetera. So there you go. So there you go. There's an example of the elements in your system. You have over to the right the worker nodes. So for example, there's a 2-node Kubernetes cluster. There's a kubelet on each of them that can create pods locally. What the API server does is somebody posts a request to the API server. Things happen. It's the schedule's watching it. Your controllers will move it further along, or the internal controllers, your external operators will move it along, and eventually they'll say, aha, I'm in a good state to actually be run. A pod is now in the state to be run. The kubelet notices it and launches the pod. And one of the things that happens is moving it along is deciding which worker node it would run on. Okay, so now that we're experts in Kubernetes, I want to share with you the Kubernetes storage journey, because if you've been following Kubernetes at all, you may be looking at things from a point in time that's no longer appropriate. So take one. The idea was, the original vision of Kubernetes is containers are cattle. Who needs persistence? You know, they'll just start and stop, and who cares? So the take one of Kubernetes was storage. Who needs storage? Take two, they realized, you know, people really need storage to do real things, and so they did the stupidest possible thing. They hard-coded the drivers into the Kubernetes core. Every single driver, every single one, an NFS driver, a Amazon driver, a Flocker driver, a Ceph driver, they were in the core. What could go wrong? Well, what could go wrong is your release cycles don't make sense. You know, you want to update your storage driver, you don't want to have to wait until the next update of Kubernetes. The other thing is that if you want to make a new storage driver, you're running inside Kubernetes. And again, what could go wrong when you're running in memory with somebody else's distributed system? The answer is a lot of bad things can happen. So that was a really, really bad idea. So they said, okay, well, take three was we'll do something called flex volumes. And flex volumes are very short-lived. They're like they're popular for like 1 or 2 versions of Kubernetes. It was kind of a kludgy idea while some standards are being flexed out. And so now we're at take 4, which is the stable, where we're going into the future, which is something called the Container Storage Initiative, which provides a mechanism for writing storage drivers that can be dynamically made available to your Kubernetes cluster. So that's what we're going to talk about. Effectively, you should think of every Kubernetes storage driver as being a CSI driver. Some are still built in. There's local hosts, there's empty dir, but you should still think of this model of CSI that I'm going to be discussing today. Going back to stage 2 in this, in stage 2, in take 2, when they had all this hard-coded stuff, the Kubernetes persistent volume object, we'll learn better what a persistent volume object is later, but that's sort of the thing that actually is kind of bound to whatever the local storage is, whether it's NFS, or it's localhost, whether it's Ceph, or etc., has lots and lots and lots of specific things to drivers that used to be there. Those are being pulled out and they will disappear soon. But right now, if you actually there's a Kubernetes command, kube cuddle explain. PV is a shorthand for persistent volume. It just shows you the YAML, and notice it goes on and on and on. So there's the Flocker driver, the Flex driver, the Fiber Channel driver, the GCE driver, the Gluster driver, the Host Pass driver, the NFS driver, the Quobyte driver. Some of these don't even exist anymore. Scale.io, Portworx, et cetera, et cetera. Very dumb. A lot of those parts of the API are going to disappear. So going back to our presentation. So finally, let's get started. Let's get started. Not quite simplest example, well, actually is the simplest example based on what I said earlier, that CSI is kind of the way to go. A pod is the unit of deployment. So let's just keep our example simple to just a pod. So what I'm saying here is I would like a pod to be running. I'm going to call it simple pod example. So I want to create a pod called simple pod example. It's going to have a container named my app that's going to be based on the BusyBox, which is a Linux distribution. And I would like to mount, like I did earlier with Docker, I'd like to have something mounted to /data. Remember I said the application designer knows what they want, where they want it, what actually happens is determined at runtime, okay? And I've run the very exciting command called sleep for a long time. What is going on? Volume mount is an element in the YAML for a pod, but it's not. It doesn't necessarily. It's not a Kubernetes object. But what it does do is it's an indirect reference to this area of the YAML of volumes. And the reason you do this indirection is, in this case, I only have one container, but if this was something that had multiple containers, but I wanted the same volume mounted to more than one container, it gives you a way to do the indirection better. So it's indirection for a case that is not being shown here, but everything, there's a ton of indirection in Kubernetes. So what it's saying is I'm saying I want to mount to /data something that I'm referring to as my data volume. And what does it say my data volume is? It says, well, my data volume is described is in a persistent volume claim. So what a persistent volume claim is it's a claim to say, I want storage. I want a persistent volume. What does that mean? Do I want it big, small? Do I want it on an SSD? Do I want an existing one with data sets and populated on it? I don't know. Well, that claim, I just know this application claims it wants some storage. And the claim, the description of what it wants, is in a separate object called the persistent volume claim object. So here we see the pod object. Oh, so sorry, one more slide. So effectively what it's saying is, once you've figured out what's that my data volume is going to be, I want to do just like I did before. I want to run whatever gets resolved to the my data PVC. We'll see that later at data, blah, blah, blah. So it's just as if I was doing this, but I can't run until I've resolved what's that my data PVC. Oh, and by the way, and also what Kubernetes node I want this run on. So here you go. So here we now go from the pod object to the persistent volume claim object. So again, the pod object refers to the excuse me, refers to the persistent volume claim object. I'm saying I'm looking for persistent volume claim object with the name my data PVC. Here's the one with the name my PVC, and it says something, something, something. These make much more sense if you're creating scratch volumes, but in this case I want to mount a data set. So I say, okay, in the persistent volume claim, it's going to be reconciled with something called my data storage class, my data SC. Again, why is this indirection there? Oopsie, why? Oopsie, sorry about that. These two objects are what are defined by the end user, the programmer, the developer on his desktop. He'll figure out how to reconcile, in his test environment, he'll reconcile what that storage class is, and we're a little ahead of the cart here, ahead of the horse here. But at runtime, it's going to be totally different. It's going to be done by some administrator. There's going to be some access, some credentials, and all this much more complicated things. So at deployment time, the cluster storage administrator specifies the storage class. So what it's saying here is, oh, that thing you want mounted, use the AuriStorDriver. And again, here's the my data storage class. Here's the storage class object, my data storage class. Using the AuriStorDriver and these parameters, mount that. Mount that. So for example, if it was NFS, the parameters would specify the machine and maybe some other parameters. Ceph specifies everything. So the parameters are very much specific to the provider. The provider is the person who wrote the driver. So think of the provider as the driver's name, the driver's typing it. Okay, so it's saying, I want to reconcile this. So again, the pod wants a volume mounted at /data. In the persistent claim, it says it needs to be resolved by the storage class object, which says I want to use the provisioner afs.csi.auristor.com, providing parameters to the driver, the CSI driver. So that's where the indirection, triggers things in the background. And then lo and behold, the driver says, okay, I know what you want. A bunch of CSI magic happens and a persistent volume object is created bound to that persistent volume claim, bound to that persistent volume claim. So it's resolved it. So now, and part and posture with that, it's also scheduled the node to a pod. We're going to go deeper into this a little later, but that's sort of the cycle, that when your pod is running, it cannot even be run. It cannot even be scheduled until the persistent volume claim is resolved to a persistent volume. And here I just say again, this is what I said earlier. So let's assume it's picked some node. If the driver says, okay, the driver actually tells us in what local directory is going to be mounted in, the driver does some local mounting, and then there's a secondary indirection where Kubernetes, when it's launching your pod, does the equivalent of the Docker run. Okay, as I described earlier. Full stop, breath. Now, for me to talk about go deeper into Kubernetes storage, I want to talk about the AFS family of file systems. For those of you who don't know AFS, listen to Tracy's talk, because she talked a lot more than I do about the history, et cetera. But effectively, the Andrew file system was the original cloud file system. It dates back to the early 80s. And it really was designed for what we're doing now, distributed processing, multi-cloud, hybrid cloud. It just does it for free. It does all that stuff for free. It's wonderful. And you know, in the Andrew Foster's family, there's effectively three. One that you, unless you work for IBM, you're never going to see, which is the original IBM AFS. It was an IBM product for a while. It's still maintained internally, but they don't sell it as a product. The Open AFS and the AuriStorFS, which is enterprise grade, that does a lot of cool stuff that the other one doesn't do. So what is the Andrew Foster system? There's really a couple of pillars. One is a global namespace, a zero client configuration global namespace. What do I mean by that? If you are on a system with an AFS or AuriStor client, you can just do this: cat/AFS/CS with zero configuration, DNS resolve, all magic happens. You just say, I've never told anything about this, but I happen to know that some file at the University of Wisconsin, the unit of administration is called the cell, so /AFS/the cell name, and the cell name is cs.wisconsin.edu. They have something called common orientation demo.doc. So this just works. So, oopsie, this just works. So it's as if it's a local file. You just use it. There's no mounting. There's no. We'll talk about authentication and credentials in a little bit, but it's just really, really cool. And I'm going to go back to that in a little bit. Oh yeah, sorry. No, sorry. The second thing is platform independent. One of the problems with distributed storage, things like NFS and CIFS, is they have their own model of how things are going to be done. So, you know, CIFS is really, you know, CIFS/Samba is, you know, really wants to be Windows. NFS really wants to be Unix. If you're crossing the line or you're using simultaneously by different kinds of clients, it's kind of funky. NFS is really hard to deal with security because it's based on user IDs and group IDs, which vary from each host. So you have to do this funky mapping. AFS is platform independent. Linux, Windows, Mac, Solaris, there's clients for it. It uses a different concept of user identity based on Kerberos credentials. So you can use the same identity across all different machines, regardless of what your host, whether you're on a Windows, Linux, or Mac. And as of a year or so ago, thank you, David Howells at Red Hat, there is now a kernel AFS driver that's deployed with some, not all yet, but some Unixes, Linuxes. It's called KAFS or CAPS. It's currently deployed with Fedora, Debian, Ubuntu, Kali, Raspberry, and Pure OS. More soon. And if you're using any of those, you create a VM, install one of those. You might have to activate it by just saying sudo syscontrol start afs.mount, but then you can just, if you do that, even without the mount, if you go sudo -mount -type afs %umich.edu : oops, something's missing, I cut and pasted wrong. You can get something in umich.edu, but if you want the global namespace, you just type the start sysctl start AFS. So now, so you get platform embedded security. If you're going to have things that are accessible all over the world by all the users, you really need security. And the security model in AFS is very cool. I'm not going to go so deeply into it. Some of these are only in AuriStorFS. It has its own access control model. Again, it's based on AFS/Kerberos credentials. AuriStor can support something called combined identity, which says, I want to only be able to access this data if I'm authenticated as this user, or authenticated as this process running on that machine. So that's something about combined identity. It has pluggable wire privacy, where the default is AE256. But if you're the NSA, it's just, if you have a you probably have a GSS implementation of your advanced security. It just works, and things like encryption at rest can be done. And the idea is every AFS cell, and a cell is sort of that administrative domain, is its own security realm. And if you're mounting things under the global namespace, the cell is what you see under /AFS/cell name. So now the meaty stuff. Volume definition number 2. This volume has nothing to do with container volumes and has nothing to do with Kubernetes volumes. These are AFS volumes. And what an AFS volume is a unit of management and policy in AFS. All it is a rooted directory tree of data. All it is a rooted directory of data that can be mounted into the global, any place you want onto the global namespace, cloned onto the global namespace. It can be mounted directly onto a local directory on your home system. AFS volume, within that directory tree of a volume, you can hard link AFS link mount to another AFS thing, and it can be to a different cell or your own cell as long as you have access to it. So it's just a rooted directory tree, but it's a policy container. It's a policy container. What do I mean by policy? I can say, okay, this volume can only have this quota, or this volume really should be running because it's really used by a lot of people. I really want to run it on 4 file servers in my New York office, 2 in my London office, 1 in my Shanghai office. Or I might want to say, you know what, this data set, this volume really cannot be housed on a server outside the US. So you label your file servers and you put that constraint on the volume. And if some administrator tries to move it there, it just won't go. So that's what an AFS volume is. Again, I've given it very short shrift, but it's really the thing behind the magic of AFS. And what Tracy said in her talk was each AFS volume logically actually is an object store, but that is a detail. It looks like a file system as far as all the the users are concerned. But because it's that, it doesn't have the problems that NFS has, where you're actually you're not exporting a drive, you're exporting a volume directly. All right. So what's an example of what you would put in a volume? I mean, so what's a volume? Why don't I just have one volume for my whole organization? Well, again, they're units of management, the units of policy. Oh, I left a very cool thing called maximal access control. If you've ever been a system administrator, you have 2 choices. You can either give all users the ability to change the ACLs on your files, or you can't. And if you give them if you don't allow them to change ACLs, then what happens? You're getting a ticket every time they want ACLs changed to change the ACLs. On the other hand, if you give them permission to change the ACLs, they say, hey, can you see the file now? How about now? You can't see the file? I'll set the permission to all. Can you see now? Great. But so can everybody on in the internet and the organization. So what you want to be able to do is take your data set, a volume, and give it a maximal access control. So I'm going to say, let's say I have a data set that's going to be bound to HR. And I'm going to do a maximal access control of people in the HR group, for example. And that way, if you can try to set the permission to something inside that volume to be everybody, but it's capped by that maximal access control. That's a very cool thing that is an AuriStor is not an open AFS. So what would be in a volume? Could be anything. A user's home directory. It could be a data set. It could be a project or research directory for shared stuff. It could be a web page. The concept of a web page that gets cloned onto somebody's web server. A lot of universities do that. That's how every user has their own web page. They do it by mounting the AFS volume inside the web server. It could be application binaries. It could have scratch space. You could use it for backup, for logs, configuration, whatever you want, but it then becomes your unit of management. All right, the next AFS thing is local cache consistency. What that means is that when you read something for the very first time from an AFS volume, it's stored in a local cache and fed to the application. The next time you do the read, it's going to read from the local cache, so without the network I/O. Why that's and this cache actually survives reboots. The reason it works is because there's a cache consistency capability that the file server has a lease with every client that is requested a leak on that data, so that if that file or region of a file changes, it tells the client whatever's in your cache is dirty. What's really cool about that is I know of at least one organization that actually boots their machines off of AFS. So for example, they have a nice big cache, and all of Linux is booted from the cache. If for some reason they upgrade or patch their Unix, then only then does it actually go to the network to get that. So you can have a whole rack and boot up, 100 VMs and have almost no network traffic, even though logically it's remotely being booted. And the cache can be large. It could be gigabytes, it could be terabytes, and you would pick that based on your use. Okay, so now finally we're ready for our very first demo. And I don't know how far I am in my slides. The slides were posted to the Slack channel, by the way. So again, the pod wants a volume call mounted at /data. It gives a persistent volume claim to be resolved by a storage class, and it provides parameters that are in the storage class object specific to the storage class type to the CSI driver. So here you see before we saw map. So here we see the mapping from the persistent claim object that says this persistent volume claim object is set by the application developer. The storage class is by the administrator, and he says, I want to mount it to an AFS driver, and here's some parameters to help you figure it out. Great. Oh, demo time. These are shorthands I use. I have aliases and scripts on my machine. I don't like typing kubectl or kubectl exec to do a shell. So these are just some abbreviations I have. So going to the demo in all right, great. So what I want to do here is I am gonna what I have here is I'm watching a bunch of different Kubernetes objects. I'm watching all the pods that are running, all the volumes that have been created, all the storage classes, the persistent volume claims, something called the persistent volume claim attachment, daemon sets, and stateful sets. You'll see that I have a controller pod running and a node pod running. I'm going to get back to that soon, assuming I don't run out of time. And so what I'm going to do is I'm going to say, okay, so I'm going to say, I want to launch that. Let me start with my PVC object. And I do that, and poof, it now should magically appear. There it is. And it's pending. It has a storage class, but it's pending because it can't resolve it to the storage class, much less resolve it to an actual volume. So now let me apply the storage class object, my data se.yaml, and poof, now there's a storage class object, and he's resolved, but he can't do anything yet. And the reason he's not doing anything yet is, well, in this case, I only have one node running in my Kubernetes cluster, but if which node the pod gets scheduled on is a function of many things. I need its GPU, I need this, I need that, I need 4 CPUs, I need this much memory, but it also is constrained by the storage, because some storage can't be accessible by some nodes. You want to preferably do it on some nodes. So until I go ahead and launch my pod, I'm saying create the pod. So now we see, boom, there's a pod that's being created. But the minute I did that, the Kubernetes scheduler, if you notice, it's scheduled to be on that machine, but it did that after, and we'll go into this deeper. It bound the claim with a brand new persistent volume object that was created, in essence, with the help of the driver. And now that it's running, if I go into simple pod.yaml, simple pod example, and again, this is some of my shorthand described it for yourself. Now I'm in that container, and I go ls data, and lo and behold, there's data there. And that data was actually coming from an AuriStorFS. Okay, so great. So that's our first demo. So what does the storage need to do? It needs to help determine which nodes in the cluster can support the requested persistent volume, the thing that has to be reconciled to volume claim. And once that's resolved and scheduled on the cluster node itself, it actually has to do the mounting. I'm not going to read it deeply now because I know I'm running out of time. So the way this is done is it's done with two driver-specific nodes, a controller service pod or a controller pod that does the logic for interacting with Kubernetes that helps provide nuggets so that the scheduler can help determine which node is a good node to run this on. There's only one controller active at any time, though you could have many running using elections, leader elections. And then there's a certain node pod running on every node. It's actually running on each node, and that's the guy that does the mounting. It has to run on every node because it has to be done by a local Linux mount. You can't do that remotely. So you need something running on each node, and that's the node service. So so the controller pod has actually, both of them have something called an identity service, which gets some plugin information, oopsie, and capabilities. The controller has to be able to answer these questions via our their gRPC calls: create a volume, publish a volume, unpublish a volume, delete the volume. The node service stage a volume, publish a volume, unstage a volume, and unpublish a volume. And we'll get into that in a minute. But so here's the life cycle. The boxes describe the potential states of a persistent volume that's being created, persistent volume object, the Kubernetes object, not the physical storage. So the controller service is asked to create the volume. Once it answers that, it gets published. It goes to a node ready state. Then it goes to the node itself, and it says stage it on the node, and then finally it says publish on the node. And when it's deleted, it does the same thing in the opposite direction. So let's, but you see it just like everything in Kubernetes. Everything is ephemeral. You know, your controllers and your node controllers can just die. So what happens is in the CSI API, there's a kind of a key value, a name value pair, string pair called a volume context that gets passed along, gets created and passed along in each of the steps we just saw. There's also something called a publish context. So what happens is, remember our storage class object? It had some parameters. What happens is Kubernetes, once it sees, aha, there's a persistent volume claim that's bound locked to a that has a valid storage class object, it takes it creates in growth, in the process of being brought to existence, a persistent volume object. It has a name, it has an ID, passes that information to your creates volume method of your controller. What it then does is it then builds that volume context. And typically in a driver, you'll take some of the parameters and put them in the context. So you move those parameters in context, you'll do some validation, etc. And so the input are these, the output is a volume context. At some point later, it decides it's ready. The scheduler says, okay. Oh, and in that I also give them nuggets, crumbs that will help the scheduler decide what node to run to schedule the pod on. So it takes this, it takes my crumbs. It finally decides that it's time to schedule that pod. So it says, hey volume, hey, I'm gonna augment the volume context that you gave me a little bit. I've decided on the node, and I go, hey controller, I'm gonna publish this, and this is the node it's gonna be going on. So the first one, I don't know what node. Now it's resolved the node. The scheduler has resolved the node, and it creates at that point a publish context, which is dangled later on. Then on the node, it calls the node services node stage volume with this augmented volume context, and that's where it sort of does some validation. This is I'm not going to go into that. And then finally publish. And when it says publish, it says, and this is the path I want you to mount your storage on, so that I could then mount that to the container. So, so remember what the pod wanted? The pod wanted to have something put at data. And what did the storage class want? It said, I wanted some storage, some AuriStor storage with this parameters. So you mix them together, and what happens is, sort of the bottom of that thing is this data goes into ... onto the local node, everything's resolved. Notice the volume context has some storage parameters and the target path, right? So what happens is he takes that, and during the storage driver's node publish, it actually does the mount. It actually does the mount. Remember, my parameters were AuriStor cell and AuriStor volume. This is how you mount an AuriStor volume on that cell and that volume name to the target path they gave me. And when I return from publish, Kubernetes knows, aha, now I'm ready to go. So it creates, it doesn't create it. I now have a ready persistent volume object. So on that local node, worker node, it can actually do the equivalent of Docker run. That directory told me the target path to, the /data. Okay, so that's how it works. Just fleshing out that whole diagram together, the pod wants something mounted at data, a transient persistent volume claim connected to described by a volume claim, which is resolved by a storage class, which provides parameters to the driver, and with some Kubernetes, some crumbs about topology and other things. The persistent volume gets into its ready state. When it's in a ready state, and it's bound to a persistent volume claim, and there's an object in the middle called the persistent attachment volume attachment. And you may have noticed that if I go up here, I have my persistent volume claim, my persistent volume attachment, and my storage class. And so I don't have the full display, but the way it works is a persistent volume object has effectively a reference to the persistent volume claim. The persistent volume attachment, the volume attachment has an internal reference to the persistent volume. The storage class can be used over and over again. The storage class can be used with many volume claims. All right, so that's a one-to-many relationship. Everything else is a one-to-one relationship. Okay, so that is the bulk of my talk. And I've got a few minutes left. So what I'd like to do now is talk about some special, unique capabilities of AuriStor. So here is sort of a fleshed out, all the parameters, all the parameters, all the interesting parameters, some of the interesting parameters for an AuriStor, parameters to create mount an AuriStor volume to a Kubernetes pod. There's a volume type, a cell name, a volume name, volume proximity required, schedule deferred type, and volume prefix, What's going on here? Well, normal is just I want to mount the AuriStor volume called Jerko in that cell to wherever you get it, resolve it. If I want scratch memory, that's scratch storage that's going to be deleted when I'm done, I say the type is scratch, but because scratch is kind of created locally, it generates a name, the driver generates a name, so you want to, for manager purposes, give a prefix for that name. So it'll be scratchy dash, ABCD 01, blah, blah, blah. Okay, so I don't specify a name, but I do specify the cell. I just specify a prefix. Stateful sets are the things that can scale up and scale down, and they're ordered. So if you run a stateful set with 5 replicas, there is a number 0, number 1, number 2, number 3, number 4, number 5, and you want to make sure the data, the disk gets mapped to the right one. So for example, if you have 5 running and you've allocated 5, and then 3 dies, when 3 gets restarted, you want it to be mapped to the storage that the one that died was mapped to. So here I'm just saying, what's the volume type? It's a type create if it doesn't exist. And I want here I'm not specifying a volume name like before, but I'm saying a volume prefix, my data set. So it's assuming there'll be an AuriStor volume called my dataset -0 -1 -2 -3 -4. Alternatively, you can provide a list of names. So, you know, it will map the 0th one to New York dataset, the first one to Miami dataset, and the second one to Salt Lake. The last demo, and I think I'm very close to being over, but I have 2 more slides. This is a very cool thing because you have file servers all over the world. Not every file server is running a Kubernetes cluster. You might be running a Kubernetes cluster, you know, in AWS, but you have perhaps some volumes that are in my data center. So I might say, look, I want to run a job, but I don't want this job started unless that volume is near some definition of near the pod in the cluster. So I might have a file server in my cluster. So what happens is when you give the claim that I want proximity and I'm willing to wait, your pod won't get scheduled until that data has been replicated from wherever it was into whatever the definition you've given from near the file server is. So that's great. It's just deferred. It's deferred starting. Alternatively, because remember, AFS is access transparent, so you can actually access the volume as it's being relocated from one place to the other. So you can say, I want to do exactly that, but start immediately. So it'll be slower because it's accessing the data over the network all the way back to New York, and I'm running in Chicago, but it's in the background, bringing that into my cluster, and once it's there, it'll then do the IO faster into the cluster. So it's kind of a, you know, start right away, but you just know you're going to get faster once the data has been migrated, unless it's already there, in which case you start immediately. All right, I think that's my last slide. Couple of links, you know, AuriStor file system, Kubernetes documentation, CSI specifications, my email. Feel free to reach out to me either via email or right now in the Slack channel for room 4, or ask questions now, because Naveem hasn't kicked me out yet.
Sure. Thank you, Gerry. It's a great presentation.